Fluid. A fluid is any state of matter that has no fixed shape. Again, has no fixed shape, where the molecules are able to move past one another. And fluids are categorized as either gases or liquids. Now, to subcategorize or subdefine, a liquid is a substance with a definite volume but with no definite shape, and it traditionally takes the shape of the container. For example, if you pour water into a cup, the water takes the shape of the cup itself. Now, a gas, though, is a substance with neither definite volume nor shape. So a gas will keep expanding and those molecules will keep moving further and further apart. Now, if you put it into a container, if you fill up a hot air balloon, the gas will obviously have some sort of limitation on it. So in this image here, we could actually say that cats do exhibit properties of a liquid. In this case, okay, because we see that the cat does take the shape of the container, but obviously a cat doesn't have freely flowing molecules and a non-fixed shape. So it's obviously not a liquid, but this cat happens to take the shape of the container in all three of these scenarios. So the joke is that it adapts to its container. Next, we'll take a look at the word density. And the word density, really, another word for it is concentration. Concentration, you've heard of that in chemistry before, where you look at the concentration of an acid or a base in a substance. The density really defined is the quantity or of a substance or entity in a given amount of space. So an example of density that you wouldn't think of is something like population density. The population density of New York is much greater than the population density of, say, Idaho, where there's far fewer people in a given location. Okay, so in a given amount of space. So density can range. Now, mass density is what you hear a lot of in science. And mass density is the mass per unit volume. And here it is right here. So rho is our density, m is mass, and v is our volume. And density is given in kilograms per cubic meter. Again, because mass is measured in kilograms, and volume is measured in meter times meter times meter, or cubic meter. Now, something to note is that most solids and liquids are incompressible, which means independent of the pressure, while gases are not, and they could have a range of densities based on the pressure. So if you think about it, if you have a gas in a closed container, like a tire, okay, and there's a certain amount of gas molecules in here, these molecules can get closer and closer as you pump more gas into the tire. And the molecules, there'll be more molecules that get closer and closer. And what this does is this allows the gas to be compressed, or meaning it has a higher density now. Okay, so as the pressure increases, the density will also increase for a gas. And that's in a tire. Whereas a liquid, see, we've got a cup of water here. If you add more water to that, well, it's just going to fill up the cup more. It's not going to compress the water below it and make it a higher density, okay? And this, again, is most solids and liquids are not compressible. There are obvious exceptions, such as a solid like balsa wood. Balsa wood is extremely easy to deform. So a piece of balsa wood, you could take your fingernail and make an indent on here, and it will remain indented. You could take a vice grip and squeeze down here and here, and this end might suddenly be slanted. So this end might look like this. Okay? You take a vise and press in on this end over here, and suddenly, instead of it looking like this end has now been crimped. And what that'll do is it'll obviously change the volume, it compresses the actual solid, and as a result, it changes the density of the wood itself by compressing it. So example 1 says the density of a meteorite is 1,250 kilograms per cubic meter, and its mass is 250 kilograms. What volume would the object displaced if submerged in a tank of water? So let's start by listing what we know. We know the density of the meteorite is 1,250 kilograms per cubic meter. And we know the mass of the meteorite is 250 kilograms. So right away we could find the volume. We could find that volume of the meteorite itself. So knowing that density equals mass over volume, we can solve for volume, getting volume equals mass over density. So take the mass of 250 over the density of 1250, giving us a volume of 0.2 cubic meters. How do I know my units are cubic meters? A, because it's volume, and B, because we're going to divide kilograms divided by kilograms per meter cubed, right? Our formula. These units are going to be kg, these are going to be kg per meter cubed. Cancel, cancel. Put a 1 in those spots to reduce. Well, when you divide by a fraction, you multiply by the reciprocal. So when you're dividing by 1 over meter cubed, it really becomes just meter cubed. Now we know this is right because of our displacement principle, which says that if we have a certain amount of water and we take an object and drop it into that water, what will happen is the water level will rise to a new height, and that amount of water that has been displaced is equal to the volume of the object when it's fully submerged. Next, we need to define the buoyant force, and the buoyant force is a reactive force similar to the normal force that acts upward on an object submerged in a liquid or floating on its surface. Okay, submerged in a fluid, rather not liquid, a fluid, or floating on its surface. Now, what do we have to know about this? Well, think about it like gravity's pushing down, something has to push back up, So think about when you're, swimming in the ocean. You don't feel as heavy as you actually are when you're swimming in the ocean. Now, sometimes if there's enough salt, the water, you could stay on top of it. But other times you'll be in salt water where you're kind of like feeling like you weigh less. Well, that's called your apparent weight. And this is the weight felt by an object immersed in a fluid. So if you're a person and you're swimming underwater, okay, flapping your hands back and forth, swimming, and you're moving through the water, here you're in the water, you don't feel like the actual weight. You don't feel the weight that you are. So say you're 150 pounds, you're not going to feel like you're moving 150 pounds. You're going to feel a lot less because of the buoyant force. So if we think about this just by looking at like a simple free body diagram, we can think about the fact that the buoyant force pushes up similar to the normal force. That's why we put this here. And gravity pulls down. So what would your apparent weight be? It would be the difference in these two. So if you normally weighed 150 pounds, but the buoyant force was pushing back up with 20 pounds, you then weigh 130 pounds. Okay, the difference between them is the apparent weight of an object. Now, Archimedes' principle tells us that any object completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid displaced. Let's discuss that because that's a bit confusing. So here's the water level. Object is not submerged. Now it's partially submerged, and a certain amount of water has come out of that as a result. That water is still streaming over the side here. The mass of this water times gravity gives us the weight of the water. Well, the weight of that water, Fg I should really write to be consistent, W is work. The weight of that water is equal to the buoyant force pushing back up. So as it gets submerged more and more, until it's fully submerged, the buoyant force keeps increasing. So there's no buoyant force here, there's some buoyant force here, and there's a maximum amount of buoyant force here. Because once this object is submerged, whether it's all the way at the bottom or not, here it's still fully submerged. So it still displaces the same amount of water. This amount of water is the max amount of water that this object can displace. Well, it turns out that the volume of that water, of that fluid, is equal to the volume of the object in the third case. The reason is because it's fully submerged. So when an object is fully submerged, the amount of water that would come over the top would be the exact amount of water that is equal to the volume of the object itself. So what we can say here is this. We can say that the force of buoyancy, again, is equal to the weight of the water, right? The buoyant force is equal to the weight of the fluid. So how do you write the weight of a fluid? Well, I'm going to put Fg, I'm going to write the word fluid here. Now, the force of gravity is always the mass of the water, or the fluid, times gravity. That's this from here, mass times gravity. But we don't have the mass. We usually have the density and the volume in these problems, not necessarily mass of fluid substance. So let's replace this with some equivalent expression. Well, since density equals mass over volume, we could solve for mass, getting mass equals density times volume. So plugging in density times volume in for this mass right here. And doing so gives us density times volume instead of mass. I'm going to put F's for the fluid times G. Okay, so the force of buoyancy that you're always going to experience by a given object, whether it's partially submerged or fully submerged, is equal to the density of the fluid that you're submerging it in times the volume of the fluid that has been displaced, which is really saying the volume of the object that's currently submerged, whether it's part or the whole, times gravity. Let's take a look at our units to make sure they match up in this case. Units of force should be newtons. Units of density are kilograms per cubic meter. Units of volume are cubic meter. Units of gravity are meters per second squared. Well, the meters cubed cancel. We're left with kilogram meters per second squared, which is indeed a newton. Next, let's go ahead and take a look at sinking versus floating. So we have two scenarios here, and in either scenario, what we know is that the object has gravity pulling down and the buoyant force pushing up. Those are the only forces acting on this object. Gravity is pulling it down, and the buoyant force is pushing it back up. Now, right away say to yourself, and make sense of it, if gravity is more than the buoyant force, it's going to sink, meaning it pulls down more. If the buoyant force can be equal and opposite to gravity, it will cause it to stay on the surface or float. The buoyant force is not really going to be greater than gravity, except at certain intermediate stages, if there's an object that's forced to the bottom and then released, causing it to launch up. Then for a little while there, the force of buoyancy will be greater than gravity. But once it comes to rest at the top of the surface, once the egg is sitting at the top of the surface of the object, the buoyant force and gravity are balanced out. So what we can say is this: F net equals FB minus FG. Now, when it's floating, there's a balance, so there is no F net. And this tells us that the force of buoyancy equals the force of gravity, and that is absolutely true when it's floating. But when it's sinking, the only way something can be sinking is if the weight is greater than the buoyancy force. Well, take a look at this. If this number is bigger than this number, you're taking a big number and subtracting it from a smaller number. So like 3 minus 5, you're going to get a negative answer. So what we can say here is that FB minus FG is less than 0. It'll be negative when it's sinking, and that makes sense, because really this equals MA, and if it's sinking downward, then the acceleration will be down, thus making it negative, or less than 0. But now what we want to do is go ahead and move this over and say this, which makes sense. Okay? Again, if gravity is greater than the buoyant force, it sinks. Or if the buoyant force is less than gravity, it sinks. But what we can do at this next part is prove that this applies to densities as well. And the way we can do this is by substituting what we know. So I'll do it on the sinking side, and we'll do the analogous part on the floating side. So here, the buoyancy force is rho F VF times G, less than rho O VO G. Well, where does rho O VO G come from? Well, that comes from the fact that the mass times gravity is really the weight. That's really what it is. But remember that mass is density times volume. Now, if the object is submerged, what's going to happen in this problem? Well, what you're going to notice is that the volumes are the same. The volume of the amount of fluid that it's pushed aside has to be equal to the volume of the object itself, because it's sinking, it's underwater. So we can just call those V's now. Just call each of them V. If V times G is on both sides, we can cancel out because they're all multipliers, giving us rho F less than rho 0. Let's make sense of this. If the density of the object is greater than the density of the fluid, well, that means it's going to sink, and that's what we had, sinking. Or if you could say the density of the fluid is less than the density of the object, it also sinks. Now in this case it gets a little bit tricky. Consider the fact that, well, at first it looks like we're going to get an answer here. We have to do the same process of rho F equal to rho 0. Okay, which tells us that when the densities are equal, it'll be floating. Well, that's more like a state of suspension. The object will be suspended somewhere in the fluid if it's equal density. It could be anywhere in the fluid, really. Now, the minute the density of the fluid becomes greater than the density of the object, right, the opposite of this case over here, when the fluid has more density than the object is less dense, it's going to start to come up to the surface and float. So this object will move up and it will begin to float. Now that'll mess around with our volume idea that the volumes were the same, but that's okay for now because this also changed. So this is a state of suspension right here, meaning the object is suspended in limbo. You can call that floating still. This is floating on the surface. This is true when the object is sunk. Next, let's take a look at an egg and water buoyancy experiment. So all you need to do is just fill a cup with water and place an egg in the cup. So let's put a cup here, put a cup here, and put a cup here. Put an egg in the cup, filled it with water. All right, there's the water level. Now, what we're going to do is we're going to notice that this egg sinks in the water. Thus, the density of the egg must be greater than that of the water, which is fine. But then what we're going to do is add a bunch of salt to this water, which keeps the water at approximately the same height, because the salt begins to get dissolved into the water. Now, over here on the left again, we have the density of the object is clearly greater than the density of the fluid, and thus it sinks, right? But if I keep adding salt to the water here, what I'm going to be doing is I'm going to be increasing the density of the fluid, because I'm adding mass. I'm adding all this mass, all these salt particles, but I'm not really increasing the volume. So this will increase the density of the fluid until eventually the object will no longer be greater in density than the fluid, but it'll be equal to the fluid density, and the egg will start to become suspended. And then eventually what will happen is this. The object's density will be less than the fluid if we keep adding salt, and we'll see that the egg will start to float actually. And what's interesting to see here is this. If we take a look at our equations here, we can see clearly that the buoyancy force in this case and in this case is equal to gravity, right? So in this case, the buoyancy is less than gravity, it sinks. Here, buoyancy is equal to gravity. Well, over here, once it's settled out from like popping up above the water, the buoyancy is still equal to gravity. Well, that doesn't make much sense, because we know that buoyancy is rho F V F G, and that equals a fixed number, whatever the weight is. Well, suddenly it's still rho F V F and G, and that also equals that same fixed number. But what we know is that the density of the fluid increased from here to here because we added salt, so the fluid density went up a lot. So something has to happen to keep this to be fixed. Well, that is because the volume of the fluid displaced went down. That's because now look at the egg. It's kind of above the surface here, so only the bottom part of the egg here is displacing fluid. So VF goes down as a result, mathematically, because rho F goes up. So in that last example there, we saw that the fluid could have a variable density as we continue to add salt, and there are other examples of things, many with variable densities. For example, fish. Like, for example, a blowfish. A fish will inflate to decrease its density, causing it to rise up toward the surface of the water. Humans, if you inhale, take a deep breath and hold it in, you now have a lower density right now because you have a lot more volume than you normally have with the same mass. Liquids, as we saw a moment ago, and a lot of the time liquid variable densities are used in forensic science to determine the density of an unknown substance. It can be placed into a graduated cylinder that has a differential density. So the density at the bottom of the graduated cylinder, say it's filled to here, is very high density fluid, lower density, even lower, and even lowest. So you have liquids with different densities and different layers, and say you wanted to find the density of a piece of hair, okay, because it helps you determine who the suspect was. Well, depending on where that hair, you drop the piece of hair, see that's the hair, you drop the piece of hair in, say the hair levels off right here. Well, that means that the density of the hair is somewhere between whatever this reading is and whatever this reading is. It's a little bit less dense than this reading, or a little bit more dense than this reading. And you might have graduations along the side to show that. And finally, if we look at something like a hot air balloon, okay, a hot air balloon, as the amount of heat changes in the air balloon, the density of that balloon will change as well. And temperature and density are related to one another. Let's take a look at example 2 here. We're going to calculate the actual weight, the buoyant force, the apparent weight of a 5 times 10 to the negative 5 cubic meter iron ball floating at rest in mercury. And then we're going to say how much of the ball's volume is actually floating. So what we have here is a chamber of mercury with an iron ball floating on the surface. Now, let's say that most of the iron ball is below the surface. We're going to figure out how much of the volume of the ball is floating. So eventually, we're going to be trying to figure out this shaded region right here in 3 dimensions, obviously. But before that, let's find the actual weight, the buoyant force, and the apparent weight of this object. So first, the actual weight of it is determined by saying, well, the weight of an object, Fg, equals mg. But we don't have mass in this problem at all. Okay, we're not given mass. We do have the density of iron as a solid. And we do have the density, let's put it here, of the fluid, which is mercury, in the liquid form. So what we can do is we could say, let's go back to our general formula. Rho equals m over v. Solve for m equals rho v. We'll take this quantity and plug it in right here. So the weight of the ball bearing is rho O, meaning the density of the object, times the volume of the object times gravity. Now to continue, we're going to need to actually know these values. So the density of iron as a solid is 7.86 times 10 to the third kilograms per cubic meter. The density of mercury in the liquid form is 13.6 times 10 to the third kilograms per cubic meter. So we take our values and we can figure out the weight of the object. Again, multiplying P0 times the volume. Well, here's the volume right here. How do I know this is the volume? Take a look at the units of it. Cubic meters, that's volume. So that's going to go in here for V0 and then times 9.81. That gives us a value of 3.86 newtons. Now, I'm really getting the magnitude of the actual weight, right? Because it's acting down. So we'd say it's negative, but in a moment we're going to look at a free body diagram. So I'm just going to look at the magnitude for now. The second part says to find the buoyant force. Well, if this object is at rest, gravity acts down, and the buoyant force acts up. And they're equal and opposite each other if it's at rest. Because remember, if something is at rest, F net equals ma, or just 0. So we get FB minus Fg equals 0, or simply that the buoyant force is equal to the gravitational force, just in the opposite direction. So it turns out that the buoyant force is also 3.86 newtons. Okay, acting upward. So what would the apparent weight be? Apparent weight is the weight that you feel like. Well, if gravity is pulling down 3.86, buoyancy is pushing up with 3.86, the apparent weight is just 0. The apparent weight is equal to 0 newtons. And this is always true for objects that float on the surface of a fluid. The last part asks us to see how much of the ball's volume is floating. And to do this, what we can do is really find out how much of the ball is submerged. We know the total volume of the ball. Say, for the sake of this is under the water level. So if we can find out how much is submerged and subtract that quantity from the total, what we'll get is the amount of the volume that is currently floating. Well, the amount of the volume that is submerged is VF, really. And that's weird to think about, but that's what it is. The volume of the fluid that has been displaced, right? The water, here's the water level, or the mercury level, whatever it is. The fluid that has been displaced is really equal to the volume under the water. So when we're trying to find this volume submerged, it's really like saying find VF. Okay, and we know that our formula for buoyancy is rho F VF G. That's our buoyancy formula. Well, we know the force of buoyancy right here. Let's just go ahead and solve for VF. And if we plug in the force of buoyancy here, the force of buoyancy is 3.86. The density of the fluid, which is mercury, is 13.6 times 10 to the third. And we multiply that by our gravitational constant. That gives us a final value of 2.9 times 10 to the negative fifth cubic meters. This is the amount of volume that is underwater. But we don't want that. We want the total volume that's exposed. So we take the original total volume of the ball bearing. This is not a 12, it's a 2. We take the original volume, 5 times 10 to the negative 5 cubic meters, the total, minus off this amount that's submerged, 2.9 times 10 to the negative 5 cubic meters, giving us the amount of the volume that is exposed to the air, which would be 2.1 times 10 to the negative 5th cubic meters. So this is a really good application that we can apply here, and think about buoys in the ocean. Buoys are usually chained down, but their density is a specific value so that part of it is exposed above the water level, so it helps boaters navigate through the ocean. We'll see in a minute what happens when chains hold it down. We have a force of tension there too. That'll be in the next example now. Example 3. An object with a density greater than salt water is dropped into the ocean. So it's going to sink if it's got a density greater than salt water. So already we got the ocean here. This object has sunk to the bottom. It is anchored to the ocean floor. So we anchor it with some sort of chain. And then it's inflated. So it's inflated to a bigger size suddenly. So now we've got an object like this size, still anchored though, to a density or causing its density to decrease to a value less than salt water. So now it wants to return back up to the surface. So these chains are holding it down. The chain that is anchored experiences tension in the links. What is the force of tension if the density of the object is 500 kilograms per cubic meter and its volume is 20 cubic meters? 20 cubic meters. Now at first you might wonder, well, is this the density of the object before it gets inflated or after? But you need to really use context clues here. We're remembering that the fluid we're in is salt water, which has a density of 1025 kilograms per cubic meter. Now, if this is the density of the object and it's less than this number, an object with this density will float in salt water because it's less dense. So this means that has to be the density after it's been inflated. Okay, after it's been inflated. If this were the density before it was inflated, it would have never made it down to the bottom in the first place. So this is the volume of the object after it's been inflated. And that's what we need to know because we're looking at a free body diagram of forces on this object. The chains are pulling it down, so there's tension. The gravitational force is pulling down, and then buoyancy is pushing back up. And remember, this is after it's been inflated because we're trying to find the tension in the cords. If it wasn't inflated, would there be any tension? No, there'd be no tension in those chains. So let's go ahead and take a look. So we've got the density of the fluid already. Okay? We've got the density of the object after it's been inflated. We've got the volume of the object after it's been inflated. 20 cubic meters. Okay? Now, if it's completely submerged under the water, that's also the volume of the fluid that's been displaced. Remember, if an object is completely submerged underwater, the amount of water it's displaced is equal to the object's volume itself. So we can say those things are equal. So we've got 4 knowns here, right? We've got 1, 2, 3, 4 knowns. We also know gravity. So let's write a free body diagram equation from this, or a force equation. So we use Newton's laws. F net equals ma. Now, had this object been rising up to the surface, you'd have acceleration, and you couldn't just drop this off. But since it's anchored down, it's 0. And the sum of the forces, we've got buoyancy acting up, gravity pulling down, tension pulling down, and again, it's not moving, so that equals 0. Now, at this point in time, what we can do is start substituting. Remember, our force of buoyancy is always rho f VFG. Our force of gravity, or any weight on an object, is really the mass of the object times gravity, minus the force of tension equals 0. So as we're trying to find the force of tension, I'm going to start by adding it over here. So move this over by adding. I'm then going to replace, I don't know what the mass of the object is, but I know the object's density after inflated, and I know the volume of the object. So I'm going to do this now. Okay, at this point I could plug everything in, but I could also simplify it even further, because since the v's are the same, I could just call it v. Alright? Again, that's only because V0 and Vf are the same when an object is fully submerged. I can then take out a Vg over here, leaving behind rho f minus rho 0 equals the force of tension. There's no need to really factor that out. Mathematically, you could just plug in, but it's the same answer. The reason I want to show that, though, is because we did this earlier in the lesson where we factored this out and the Vg values canceled on both sides. But in this case, there's not a 0 over here, so I can't just drop this off anymore to solve. But I can clearly realize that I know this, I know this, I know these. This is what I'm solving for. So plugging in, the volume is 20 cubic meters of the object and the water displaced. Force of gravity is not, or acceleration due to gravity is 9.81 meters per second squared. And then we're going to subtract our two densities. We've got 1025, and that's in kilograms per cubic meter, minus 500, and that's also in kilograms per cubic meter. And that equals the force of tension. Well, let's take a look at this. We're going to get a positive answer clearly because our force of tension was drawn down, which is the correct direction it should be drawn in. And we get a positive answer because the difference here is positive. Imagine the object had more density than the fluid. Well, that's what it started with, right? It would sink. And as a result, if this density was greater than this density, this number would become negative, which would mean our force of tension would be negative. Well, that would be like this. Here's the ocean floor. Imagine the object sunk all the way and it was still anchored down. If it weighed enough, if there was enough density to it, maybe it would indent into the ground. And the object, instead of being up, would be like this. Like kind of leaving an indentation. Well, then the chains would kind of be holding it up from falling into the ground, which is why if this density were greater than this density, then the force of tension you'll get would be negative, indicating that because we showed tension pulling down, if this object sunk far enough, tension would then be pulling up. Okay, but we can see that our answer is right because we get a positive value here. Our final solution here is 103,005 newtons of force. Now remember, if there were more than one chain at the bottom, say there were 2 or 3 chains, you'd have to split that accordingly. So each of them would have a third or maybe a half of the amount of force felt on that chain itself.